Hey guys, so today we're going to be starting our second unit, which is all about gases. This is a really short unit. There's only like 4 lessons or something like that. And today we're going to be going over something called the kinetic molecular theory, which describes how gases behave. So the kinetic molecular theory that we're going to be looking at, essentially what you need to know about it is why we care about the kinetic molecular theory, what the point of the kinetic molecular theory is, the 4 different assumptions of the kinetic molecular theory, and how those assumptions don't really hold true for real gases. They hold true for ideal gases, but not actually the gases that exist in the real world. So like I said, the kinetic molecular theory describes how gases behave, specifically how their molecules behave. And we do this to kind of relate the different properties of gases, like their volume, temperature, and pressure, to their behavior. It also helps us describe and explain how different gas molecules interact with one another. And like I said, it is based on a couple different assumptions. The first assumption is that all molecules of gas are point masses, meaning that we're assuming that molecules of gas have no volume and don't take up any space. The second assumption is that there are no forces of attraction between molecules of gas. So 2 molecules of gas can go right by each other, and there will be no type of force of interaction between those 2 molecules. The third assumption is that molecules of gas move randomly and will only change direction if they collide with something, whether that be another molecule of gas or like the wall of a container. Other than that, they'll just move in a straight line, hit something, bounce off, move in a straight line again. And the fourth assumption is that kinetic energy is conserved when molecules of gas collide, meaning that there's no loss of kinetic energy. Now, as we go through this and kind of explain all of these, you'll start maybe seeing why they don't always apply in real life. So the assumption that gas molecules are point masses is essentially, we can use this assumption because gas molecules are so far apart that gases are mostly empty space. That's why we can like move through the air so easily, because it's mostly empty space with gas molecules super spread out. So the actual volume that those gas molecules take up is super, super tiny compared to the whole volume of gas. The volume of gas in the room that I'm in right now is quite large. The actual volume that the individual molecules take up is so tiny that we essentially say it's negligible. It's not worth caring about. We're just going to assume or pretend that those gas molecules have no volume and take up no space whatsoever, because that'll make our life easier if they don't have any volume. It'll make our calculations easier, I should say. This is also the reason why gases are so compressible. We can squeeze a large volume of gas into a very tiny space and put it under a lot of pressure because those gas molecules are so far apart. So when we're squeezing or compressing a gas, we're really just getting rid of some of that empty space. Assumption number 2 is that there are no forces of attraction between gas molecules. And the reason this assumption is kind of valid is because any bonds that do exist between molecules of gas are super, super weak. There are actually forces of attraction between gas molecules, but they're so weak, they don't really affect the gas molecule behavior very much. And therefore, we say that they're negligible and we pretend that they don't exist at all. This is the reason why gas molecules can spread out so far, because they don't have much of a force of attraction between them. That force of attraction would hold them together if it existed. So gas molecules will spread out, they will diffuse until they fill an entire container because those forces of attraction are so weak. And again, we just assume or pretend that those forces of attraction don't exist at all. If this assumption was 100% true, it would mean that gases could never condense into a liquid, no matter how cold it got or how much pressure you put them under. And that's why we know that this assumption isn't actually true for real gases out in the world, because if you cool down a gas enough or you put it under enough pressure, it will eventually condense into a liquid, and it shouldn't according to this assumption. But under normal circumstances, room temperature, normal atmospheric pressure, those forces of attraction are so weak that we can assume they don't exist. Assumption number 3, again, that's that gas molecules will move randomly and only change direction if they collide with something. And again, that's just kind of this idea that gas molecules should always be moving in straight line. You should never see a curved line for the movement of a gas molecule. And the last assumption, that kinetic energy is conserved when gas molecules collide. Another way of saying that is that we're assuming that the collisions between gas molecules are elastic. So they essentially just bounce off each other without losing any of their speed, which would be related to their kinetic energy. So normally, if you think of like two cars colliding, they would collide and then slow down. But with gas molecules, we're assuming it's completely elastic. They just bounce off each other, go off in different directions without losing any of their speed. If that's the case, the only thing that should affect the kinetic energy of the gas molecules is temperature, not collisions. So collisions do not change their kinetic energy, but temperature would. So if you increase the temperature, you would also increase their kinetic energy. So ideal gases are gases that perfectly fit all of these assumptions. They follow all of the gas laws perfectly. They make our calculations super, super easy. And all of the different gas laws that describe the relationship between temperature, pressure, and volume would work just the way we want them to. So ideal gases have no volume, have no forces of attraction, have elastic conditions, all of that kind of stuff. Real gases, the gases that exist in the world around us, are not ideal. They don't perfectly follow the assumptions of the KMT. In fact, most of the assumptions don't really work at all. However, they're close enough, real gases are close enough to ideal gases under normal circumstances that we pretend that they're ideal for the sake of our calculations. Again, when you get to extreme temperatures or extreme pressures, real gases start to behave less like ideal gases, especially if we're talking about cooling gases down a lot or putting them under a lot of pressure, then the rules really start to fall apart for our real gases. So let's look at some of the ways that real gases don't follow the KMT. First of all, real gases are not point masses. Those molecules do have a distinct volume and size. They take up space. So it is a negligible amount of space normally when they're really spread out. But certainly as those gases condense, that volume starts to matter more and more because there's less empty space the more you condense the gas. Second assumption said that there was no forces of attraction, but that's not true. There are weak forces of attraction between gas molecules. And if you lower the temperature and slow the gas molecules down, or if you increase the pressure and squeeze the gas molecules closer together, they will actually start to form stronger bonds of attraction with each other. When they're closer together, when they're not moving past each other as quickly, those forces of attraction actually start to affect the gas's behavior. And that's why under low temperature or high pressure conditions, you can get a gas to condense into a liquid because you can get those forces of attraction between the molecules to start to have a real impact on the gas. We also assumed that molecules move at random and only in straight lines, but that's also not true. Because there are forces of attraction between gas molecules, a gas molecule moving by a second gas molecule can cause that gas molecule to curve towards the first gas molecule. Essentially, their forces of attraction can curve those straight lines that we thought gas molecules would travel in. So it's not random. They are influenced by the surrounding gas molecules. And lastly, we said the kinetic energy would be perfectly conserved, that the collisions between gas molecules would be elastic, that's also not true. Those collisions are inelastic, meaning that some of that kinetic energy is lost, which of course we already know from physics in Science 10. You know, according to the second law of thermodynamics, you can never have a perfect conversion of one type of energy to another. Anytime there's an energy conversion taking place, you're always going to have some waste energy. So when those molecules collide, you are going to lose some of that kinetic energy in the form of waste energy, and the molecules will slow down. In order to speed them up again, you would have to increase the temperature to give them some thermal energy. So yeah, the collisions are not perfect. They're not elastic, they're inelastic, they will lose kinetic energy. Okay, so that is the difference between ideal and real gases. Make sure that you're familiar with all of those assumptions, how they apply to ideal gases, and how they apply to real gases, and the difference between the two. Let me know if you have any questions.